Hi, everybody, and welcome to the April edition of the Research Interest Group. Really happy to have two of our new researchers from the BU Red Hat Collaboratory here this month. Our first speaker, Michael Dietze from BU, is going to speak about prototyping a distributed asynchronous workflow for iterative near-term ecological forecasting. And our second speaker, Eshad Onbar, will be speaking about minimal mobile systems via cloud-based adaptive task processing. We have these meetings once a month, and we'll be covering new research topics next month, hoping to get through a lot of the BU Collaboratory new efforts that started this year and share those with you. So without further ado, I'll let Michael take it away.
Thanks. Let's see. Shoot. Trying to get it to share screens.
Yeah, it's always a challenge.
Into security. Oh gosh, no, it's gonna make me quit. And
I assume that he's rejoining.
Yeah, I think we have it automatically enabled to allow for screen sharing, so.
Yeah. If you need some time to fiddle with it, Michael, we could have Eshad start.
Let me try again. Okay, are we sharing now?
Yes, it says, yep, I see it.
Okay, sorry about that. I just went to share and security settings made me completely restart my whole browser, not just change some settings. So apologies for that delay. I guess I'll also say that just be upfront that this talk is going to be heavy on concepts and light on results, since we're right at the beginning of this project. We're only a couple months in. So I wanted to talk about our work in iterative near-term ecological forecasting. So just to kind of set the stage, ecology, like many other disciplines, has been undergoing a kind of a data revolution, and this has been fueled by many changes that have occurred in recent decades, whether it's been changes in underlying sensor technology, making it possible for us to measure things in real time that we used to have to go out and count by hand on clipboards and things like that, to the advent of both top-down and bottom-up observatory networks that didn't exist in our discipline. Ecology historically was a very kind of individualistic discipline where people would kind of build their careers around individual study systems rather than kind of syntheses across networks. But that's something that's really kind of taken off in the last decade or two. We've had an absolute revolution in Earth observing technologies. So building on, gosh, since the 70s, the launch of Landsat now is it unto itself is a petascale data record. But we now have not just optical remote sensing, but microwave and LiDAR and radar and gravity, and just a huge host of technologies. I think one of NASA's estimates, its Earth observation capacity a few years ago was generating multiple petabytes of data per year, and they're quickly moving into a realm where they're generating tens of petabytes of data per year, where individual missions are capable of producing petabytes of data per year. And then we've also had kind of a real revolution in the role of citizen science as well, the capacity for community projects to collect data distributed across space and time on the ground in ways that individual researchers just aren't capable of doing. And not only has these kind of changes left us as a kind of open up our field in terms of the volume of and variety of data that we're dealing with, but we've also really had a revolution in the latency of that data as well. When I was a graduate student, which was now getting a couple decades ago, getting access to data that was that someone else has already published on was itself difficult. So latency was often measured in multiple years between collection and release, and now we have many networks that are really providing data fairly close to real time. Like one of the data sources we work with in our research is one of the NOAA Earth observing weather satellites that sends us literally updates every 5 minutes for all of North America. So this advent of not just high data volume but real time data is kind of opening the door for real-time science. And it's that capacity for real-time science that's kind of really opened the door for this idea of real-time ecological forecasting, of forecasting ecological systems the way that we do weather. So this animation shows an example from my own lab of a project that does that. This is just for a single site, making a forecast of leaf on in the spring, where every single day we make a new forecast, and that forecast is updated with real-time data coming in from MODIS, which is one of NASA's satellites, as well as real-time data from phenocams, which are webcams mounted on towers. And so, yeah, we are kind of entering this kind of revolutionary capacity to kind of build forecasts. At the same time, we're entering an era where the need for such forecasts is really unprecedented. So a lot of the history of environmental management has been based on these ideas of stationarity. So we used to manage species for their historical abundances or historical ranges. We'd measure, manage watersheds for their historical flood frequencies or historical drought frequencies. We'd measure, monitor, manage ecosystems for based on historical fire frequencies and stuff like that. But with the combination of climate change and land use change and invasive species and emerging infectious disease has really put us in a place where our ability to manage environmental systems can no longer rely on the assumption of stationarity. We were not just in an era of where there's a new normal, but we're in an era where of continuous ongoing change. Kind of if you think about it from a mathematical perspective, we're in an era of transients instead of an era of steady state conditions. And so if we are going to spend the rest of our lives in transient conditions, the need for models to inform what we think is going to happen in the future to make better decisions is kind of becomes even more pressing than it ever has before. Now, one of the challenges is that a lot of the current approaches, a lot of the current modeling in environmental sciences these days has been focused on long timescale responses. So if you look in the ecological literature, you'll find lots of folks making projections of how different ecological processes will respond under different climate change scenarios projected out to 2100. Unfortunately, most land managers have no idea what to do with global resolution projections out to 2100 to make on the ground decisions. So there's this unmet need for higher frequency data. A lot of need for annual information, but often genuine need for monthly, weekly, and daily information for decision makers. And we're just not providing that right now. So that's this kind of the argument for kind of why there's this important unmet need to make ecology a more predictive science, combined with this increase in data to make this something that's more possible. So we've adopted a lot of technologies from the numerical weather forecasting community, where we start with some estimate of our understanding of the system, our current state of the system right now, let's say an initial condition. We use models to predict that out into the future probabilistically. We then compare those predictions of the future state of the system with new observations as they come in iteratively. We update that understanding and we predict again. So establishing this kind of iterative cycle of predicting and assimilating data. And I would argue that in addition to serving society, that this way of doing science is also fundamentally compatible with how we think about the scientific method as one where our forecast models embody the hypotheses of how we think systems work, and by confronting them with predictions, forecasts force us to be quantitative and specific in our predictions, and thus make predictions that are ultimately more falsifiable, while also setting up an iterative learning loop to accelerate the pace of scientific discovery. So what we've seen is over recent years this kind of a growth in forecasting capacity. So all these figures, all these images are examples of systems where folks are running iterative forecasts on daily, weekly, or monthly timescales. It spans terrestrial, freshwater, and marine systems. It spans population problems, disease problems, community dynamics problems, biogeochemical problems. And interestingly, it's not exclusively limited to just observational systems. There's also examples like this bottom center set of open top chambers where people are actually running forecasts for experimental manipulations as well, kind of combining the causal inference power of experiments with the power of forecasts. So in addition to this kind of distributed growth across the ecological community in ecological forecasting capacity, there's also been efforts to kind of bring that community together. And the big one is the launch of the Ecological Forecasting Initiative in 2018, which is a grassroots global consortium it's grown to involve over 1,000 people with mostly US origin, but chapters in Canada, Oceania, which covers Australia, New Zealand, and the Pacific Islands, and Europe, having launched in the last couple of years. And so the Ecological Forecasting Initiative is organized around a set of cross-cutting themes, which are the shared challenges faced by the forecasting community. And some of those things are, developing theory and working on, educational initiatives and informing decision making and, transferring knowledge to stakeholders. But there's also a big working group and a big emphasis on methodological improvements in cyber infrastructure. And one of the reasons for that is that the cyber infrastructure really is a bottleneck to the growth of the ecological forecasting community. So the existing suite of ecological forecasts out there largely represent boutique solutions that have been developed independently by different labs and agencies around the world without really any shared infrastructure, shared tools, or shared capacity. This has resulted in a lot of redundant efforts. So kind of a general waste of resources, or maybe not waste, but general place where resources could potentially have been used more efficiently. It also represents a fairly significant barrier to entry, both technically and financially. Ecologists don't get the same sort of computational training as engineers or even meteorologists, and so being able to set up not just the underlying models but the overall workflows to have forecasts run reliably at scale every day is non-trivial technically and financially. In addition, once you do get these systems set up, because each of them is unique, they are fairly costly to sustain, as anyone who's tried to maintain, any sort of operational workflow knows that these things keep breaking on a constant basis as libraries change and data APIs change and stuff like that. So, within the FA community, we really identified this need for community tools. And this is not just something we've identified academically, but also which is reinforced through a series of workshops that we've been doing with the US federal agencies on kind of their shared needs. And one of the ones that the agencies keep coming back to in their ecological forecasting capacity is the need for community tools. And so what we want to get to is the idea of something that is scalable, reusable, fairly modest learning curve, and by sharing things, making it ultimately cheaper for each individual team to maintain, and ultimately, hopefully, more stable, because it'll have more people using the same tools and thus, more eyes checking tools. An example of some of the progress that our community has made so far, the Ecological Forecasting Initiative together with a big NSF initiative called NEON, the National Ecological Observatory Network, which has set up a kind of a continental monitoring network across the US, Alaska, Hawaii, and Puerto Rico. We've launched this open data science challenge, asking folks to predict NEON site level observations before they're collected. And it's been open to a wide range of participants and approaches, whether it's statistical machine learning or mechanistic models. To support this, we've developed standard community formats for inputs and outputs and metadata, some basic cyber infrastructure for provisioning teams with inputs in a common format, for allowing teams to submit forecasts in a kind of containerized structure, score them, visualize them, and also running some null models to compare against. We've had, in the first two rounds, we've had over 100 teams participate, including 11 university courses, submitting over 7,000 individual forecasts, and each forecast may be a time series over numerous monitoring locations. So we actually have 2 or 3 million individual model data comparisons so far in this forecasting challenge. And so round 3 is up and running right now for this kind of set of different forecast areas. And this is kind of a quick slide kind of arguing why kind of the value of forecast having common community conventions to run not just our forecast challenge, but to kind of increase interoperability across our domain, making shared tools possible, improving dissemination, and allowing for independent validation. And this kind of argument builds on something that we're utilizing as a kind of a test bed in our Red Hat Collaboratory project, which is this kind of workflow project that I've been working on in my lab for, 14 years now, which was trying to build community tools to bring specifically terrestrial carbon cycle models and data together. And so this was the PCAM project, which is kind of an example of kind of these community cyber infrastructure projects. So this by itself supports something like 20 different models, but they are solely focused on the terrestrial carbon cycle. So just one kind of case area. So when we wrote our Red Hat Collaboratory proposal, we envisioned, I've kind of combined 2 objectives into one. So I'll say 3 objectives. One was coming up with a high-level system design for kind of a scalable set of tools that could be reused by the community, and then to kind of develop an initial test deployment of the kind of core stack of tools to get a minimal example of within a cloud-based cyber infrastructure, a test case, leveraging the existing development my team has done on PCAN, where we just want to get one model running to forecast one site, where it's taking in one input data stream, usually in this case thinking about the weather forecast as the input data stream, and one data constraint. So one thing that we can compare our forecast to iteratively update it. And with that initial test case in place, the idea is to then scale up to think about how we can schedule in a cloud-based environment, the ability to run numerous models across numerous sites with numerous different inputs and data constraints, and kind of handle the fact that these different data streams are coming in asynchronously. We want all this to be event-driven, and we want to kind of do this in a distributed manner, because as much work as we've put into the workflows like Pecan, it was it was a tool kind of initially optimized for kind of running a site here or there, and it's very linear in its operation. It doesn't process, finishes processing one thing before it goes on to processing the next thing, before it goes on to processing the next thing, and a lot of these things are actually fairly naively parallelized, but that's not how they've been implemented. As our team has dove into this, we rearranged our goals a little bit, because I guess we learned that the rest of the team, who hasn't been thinking about ecological forecasting for years, kind of didn't feel like they had the context to think about a general design to bring to the ecological forecasting community. That it made sense to dive in first with getting a test case up and running, and then with that experience in hand, to think about how to generalize that. And so we've been working with Chris Tate to kind of get the Pecan workflow, which already is kind of built into a set of Docker containers, kind of integrated into kind of the OpenShift and OpenStack framework, and then working with the BU SAIL team to kind of try to move this into the New England Research Cloud as an initial cloud-based test bed for running these. And so that's still in progress. We're still working on getting this initial test case up and running. But so since I don't have results to show from that, I'll give you kind of a bit more dive into understanding what this carbon cycle forecasting workflow consists of, and some of the work that we're doing here on the carbon cycle forecasting fits within the larger context of NASA's carbon monitoring system, which has the aim of providing carbon cycle data both for national accounting purposes, but also to inform decision making by a wide range of different stakeholders. And so the idea here is we want to say we have uncertainty in what the current carbon cycle pools and fluxes are, uncertainty about the weather forecast, uncertainty about the model parameters. We push all of these forward through a model in an ensemble mode to make an ensemble forecast, and then we constrain these with satellite-based observations of above ground biomass and leaf area, and we iterate. And so this is an example of what this looks like in a hindcast mode, where the yellow shows the forecast going forward, the new observations become available in red, and then we assimilate them in green. And one of the powers of data assimilation is we can update not just the pools that we observe, but also the ones that we don't observe. We constrain them indirectly based on their covariance structure. And then we can also harmonize across multiple data constraints. So in this case, the MODIS satellite launched in 2001, and observations on leaf area became available as an additional constraint. The same system that I'm illustrating here as a hindcast also, oops, there's supposed to be an animation there. Hello, animation. There it is. Also runs as a daily iterative forecast at a network of network of towers run by NEON, which actually is able to measure on a half-hour by half-hour basis the movement of carbon dioxide between the land and the atmosphere. So this system is running across not the NEON towers. We've also run it in a spatially distributed way across CONUS. So this bottom left shows the points where we run the forecast, and the larger image shows a kind of an interpolated map of one of the carbon cycle pools. But again, we're estimating numerous pools and fluxes simultaneously. And then within our larger carbon monitoring system effort, we've been building out a system that used 2 remote sensing data constraints to use, ultimately what will be more like a dozen data constraints. It's currently up to about 7 or 8 right now. Moving this to a North American scale, increasing the temporal resolution, and a whole bunch of other challenges we're working on. And then to wrap up, I'll come back to the big picture goal, which is to kind of get back from the pecan test case to a more general understanding of what the generic ecological forecasting workflow looks like, where you have this general problem of models being used to make forecasts, assimilating in data constraints. So we have data processing on the inputs and the constraint side, parallel model execution, and a statistical assimilation, and kind of the need to have a scheduler handling all of this in an event-driven, asynchronous manner. And also kind of on the right here, I kind of split this into tasks that really need to be automated in kind of an iterative fashion, such as the data input prep, model running, assimilation, distribution of forecasts on the backside, integration, general system integration testing, as well as a whole bunch of other things that that we run occasionally within a forecasting system, such as needing to update the whole system anytime we make model structural improvements or do recalibration and validation. I think with that, I will wrap up.
Wow. That's a lot of information in a short time. Thank you, Michael. Any questions? I have one question just from a system engineering point of view. So with so much scale, obviously, compute resources and network resources and storage resources could all be issues.
Yes.
Do you, yeah, that was my question is, do you run into problems with all of those, or is one more than others an issue, or what part of that problem you're attacking?
I would say at the moment, the biggest computational bottleneck remains model execution. But there's also a lot of low-hanging fruit. I guess that statement might be not completely fair, because I will say that most of the time we do a lot of the input and data constraint prep up front before we do long runs. I do think the easiest thing to, well, I guess stepping back, the model execution is naively parallelizable. There's a lot of resources required, but we're, even if we're running a spatial model, we're often running 100 to 200 ensemble members. So, they all run completely independently. So that's kind of a simple problem to solve conceptually, even if it, at some point you run into genuine challenges just with the number of runs we need to do. But I think where I'm kind of more interested in kind of putting effort is kind of the input processing, because, I would say we've made some fairly naive design decisions in how we originally engineered that, such that we're again doing things serially that there's no reason we have to. Like, there's no dependency among the different data constraints we have. If I need to get data from 8 different APIs for 6 satellites and 2 ground-based networks, like, I could totally ping those APIs separately. I don't have to do one at a time.
Right, wait for them to respond. Yeah.
All of these are the easy problems to solve. What worries me is that once we get all of those solved, the assimilation step is the place where the parallelization can't be done naively, because that involves, as we scale up, the size of the matrices we have to invert start getting really big. So if you look at numerical weather forecasting, where they spend most of their compute is on the assimilation step. But they're operating on a scale that we are not yet as a community. Right.
They're over in the HPC world.
Yeah, we're in an HPC world as well. But we,
yeah.
I attended a workshop a few years ago with that included some folks at NOAA from their weather forecasting community, and they were saying that their current generation forecast system assimilates something like 10 terabytes of data per day, in their next generation systems being designed to assimilate 10 terabytes of data per hour. And
Wow.
that's not a scale that ecology is operating at yet.
So,
That's amazing.
Yeah.
Michael, I'm just wondering, like, in terms of, so you've talked a lot about the compute issues, and you've talked about the scale of the storage, but just in terms of the mechanisms around the storage for retaining provenance, for understanding the relationship between compute from different, and is there standards being developed around that? Is that an area? I'm just curious where the community is going on that, if that makes any
Kind of
sense.
standards around kind of you're saying the provenance side of things?
What information you want to retain around sort of data sets? So data sets collected, and then and then somebody makes some transformations to it, which result in scientific publications. You could imagine both retaining the computation, like a containerized environment, which describes how people computed on it. You could imagine sort of retaining chains of information that resulted in different kinds of work. Is any of that make any sense, or is any of that being done?
I think it makes sense. I would say I wouldn't say there's any sort of general community consensus on how to solve these problems. I know in the numerical weather forecasting community, there's a lot they don't save just because of the scales that they're operating at. It's just it's not been practical to save, all the intermediate steps and all the details of the workflows. It's just been, assumed that you'd have to reconstruct it given the workflow and the original inputs if you needed to run something again. Within Pecan, we actually tried to pay a lot of attention to provenance tracking when we first designed the system. But that was based on technology over a dozen years ago, and so we have a central database keeping track of all the steps in our workflow, and I think the result is we over-engineered it. We ended up with a system that's very well integrated front to back, but makes it harder to use individual tools than we ever intended. And so we've actually been trying to, in some ways, make our provenance tracking a little bit more lightweight in more recent years, because we ended up with a place where you had a system was too tightly coupled and ends up kind of fragile.
That's interesting, because some of the work we've been doing in the storage front, if you look at what Larry Rudolph was talking about in the Alliance meeting, was a lot of times people don't even know what the workflows are. In a sense, different people are running different things that implicitly rely on each other, but isn't necessarily by explicitly coding. And is there ways we can actually track this information down at the bottom storage layer? It'd be very interesting as your infrastructure comes along, even for us to just start monitoring and detecting what is really going on here that may not be intentional, but is really, in fact, the workflows that are happening.
Yeah, that'd be really cool to have folks interested in taking a closer look at what we're doing.
Okay, we're going to move on to Ashid here so that we can fit both into the hour. Thanks a lot, Michael. That was really interesting. And if anybody wants to get in touch with either of these folks, you can reach out directly on the webpage, which Jen is posted in the chat, or get in touch with us and we'll connect you as well.
Yeah, that was super cool. I'd love to sort of see checkpoints as it goes along.
So Ashid. Super.
Hi, can you hear me, Heidi?
Yes. Yep, I can hear you and I can see the slides.
Great. I do have audio on one of the slides to complicate everything. How do I share audio here? Is it automatically? Let's see. Hopefully, oh, there we go. Okay, maybe it just works. More options. Okay, I'll just we'll play it, but
We'll try it and see.
sounds good. Great, so you can see my screen. Okay. Great, so hi, so good afternoon, and thanks for having me. I'm Eshid from Boston University. Very excited to share with you a bit of our research on minimal mobile systems. By mobile systems here, what I mean is systems that may be used to assist patients with daily tasks or assisted feeding, perhaps rehabilitation, wearable systems. Those are included, as well as delivery mobile systems. And this also includes an application we've been working on for a long time in our lab related to personalized assistive mobility systems. So these are some examples of the robotic mobile systems that I mean that could immensely benefit quality of life. So of course, the question is, why are these systems not yet widely available today? And I think that a key issue is their prohibitive cost and computational resources. So the systems I've shown in the previous slide can easily cost anywhere from 30K and over 100K. And here's an example of one of these mobile systems on the right, where we have Spot. So here, I'll put the laser point. This is Spot from Boston Dynamics. Depending on the configuration, can easily go for 75K or more. And then you have some more recent robots like this Unitree robot here, who is on the much cheaper end, actually generally the cheaper end of these type of systems, much lower cost, coming in at $15,000. And then on the left here, I have some very minimal Raspberry Pi type robots and a phone, of course, which is a mobile system, and can be built for about $1,000. So we can, this depends on the sensors, of course, but we can agree that the systems on the left here are much more affordable. The problem is that they often come at other costs that impact their usability. So maybe they have very low functionality or very limited battery life of 20, 30 minutes at most, as well as these actually more complex systems and more expensive systems. But this gives us some very limited window to give to these amazing applications, right? If it can only run for a few minutes before it runs out of battery. So towards cheaper, more efficient and robust real-time mobile systems, I want to kind of explore a little bit the role of the cloud. What can the cloud offer here to make these systems operate at higher capacity and robustness, particularly integration between these real-time processes that could run on the device and on the cloud. So what we do use the cloud extensively in when training these systems. So usually when training the machine learning behind the scenes, we can leverage huge amounts of compute and data. So for instance, I have on the left here a picture from Tesla AI Day, just from, I think 6 months ago, where they detailed their setup of 14,000 GPUs and over 30 petabytes of video data to train their AI, which they use both for self-driving vehicles, but also for these humanoid robots that they're building. And then on the right here, I have some example where we really have yet to hit the limit of these models. So you can see how there's on the x-axis here is number of parameters in millions, going into 500 million, 600 million. And then this is accuracy. And you can see how these models are very hungry. So no matter how much data and resources we have, they keep improving in capacity and performance, right? So ideally, especially for safety critical systems, real world, real-time systems, we want the best model, best operation we can, right? So so the cloud is often used for training. Can we use the cloud for inference? So yes, usually with applications with lower responsiveness, right? So you have some chatbots, as shown here on the left, maybe something like an image being uploaded to the cloud. You wait a little bit, there's some latency, and then you get some response, maybe from ChatGPT. But the systems from the cloud are actually starting to have more and more extension into the physical world. So on the right here, I have an example that I found on Twitter just the other day, where they built this very minimal robot. It runs in real. It may show how you might run it in real time, but note that I'll play this video. There's sound. Note how there's very high latency here. And I also want to note that there's also a communication cost that gets added in addition to any computational cost. So I'll play it.
Hello there. It's so nice to meet you. I am Fabby.
Can you hear it, by the way?
Yeah.
Okay, I'll play the whole thing so you can see it, the latency. Here we go.
Hello there. It's so nice to meet you. I am Fabby. What would you like to talk about?
Was there a secret plot from Furbies to take over the world?
I'm thinking about what you said.
So it's a Furby robot.
Almost done.
It's thinking. And
Fabby's plan to take over the world involves infiltrating households through their cute and cuddly appearance.
okay, so this is kind of how you might run it in inference. So what people usually do for these real-time systems, they just put everything on the device. So, you either have everything in the cloud or usually you run everything on the device itself. And here we have these large systems. They have battery. This comes at computation cost. So there's this extensive table here, taken from Hadidi et al., where we can see, especially in this row of average power, the power requirements for different edge devices from the left here, where it's Raspberry Pi, Jetson, and up to the more high-end GPUs. And you can see how it is a non-negligible, it's a significant increase in power when you go from this row to this row. It might double, it might even increase more than that. So this is a problem because we want bigger models, better models, but then they also come at a cost. But if you could use the cloud, then maybe you can still get away with running these larger capacity models without having to spend all this power locally. So here's another concrete example of power computation with DNN. So DNN stands for Deep Neural Network, where once we begin the inference on the device with DNNs, essentially it consumes about 50% of the power. So you can see how the power consumption kind of rise up significantly. And unfortunately, even though there are there's different types of models. So there's a model called MobileNet version 2, which is a state-of-the-art kind of edge computing model, and a ResNet model, which is more research, state-of-the-art, heavier duty model, more robust. You can see how there's really significant energy usage no matter what model you use, even at this slightly lower, maybe lower latency and lower computation model. At the same time, these are also at lower performance. So generally models that we run on an edge on like restricted devices have not only significant computational load, as shown here, but they may also decrease in performance, as shown here. Like MobileNet goes down by about 5% in this metric of segmentation. This may not seem large, but it's very easy to actually tell the difference between these models when you look at them. So you can see that there's false positives and misdetections generally compared to the higher end models. But again, we could run such models easily on the cloud, right? Like this type of larger models. So I think there is this nice opportunity here to explore a stronger integration between these edge and cloud real-time operations. And then, of course, the final dimension is communication. So when it is now feasible to transmit images, transmit data, especially with 5G, both indoor, outdoor, various functionalities that are rapidly advancing. And you can see here on the right, the kind of total latency time in seconds where you run something on the cloud or locally. So you can see how a mobile CPU has a higher latency compared to a mobile GPU, but then there is a slight communication cost shown here, like 3.2%. And then you can get away with running things very quickly on the cloud and then get back because of the reduced communication latency. And then before I show an idea of how we want to approach this problem, I want to show an example of how people might approach it today, where cloud and edge integration. So this is a cloud-only model here on the left. This is an edge-only model here, mobile-only. The integration approaches are usually quite ad hoc. So what this does is it takes part of the model and runs it locally, maybe the convolutional layers, which are very quick and efficient, and the fully connected layers, for instance, here on the cloud. This is the large chunk of the model, takes a lot of computation. And so this essentially kind of gets compressed a little bit, the data, and then gets sent to the cloud and back. But I have some reservations against such approaches, because what if we don't have time to wait to the cloud in this specific safety critical situation? So this integration is fixed, it's not dynamic. There may be some scenarios where and we would like to make it task dependent ideally, right? Especially if we care about efficiency and operation. What if the cloud can run a different type of model that is much larger and more robust? So this kind of ties them in a way that's very ad hoc and limiting. And then maybe sometimes it might be just good to send everything to the cloud, right? So we can save so much energy locally if we just compute everything on the cloud. So we can run bigger, better models. So I want to present kind of our current thought about it and some preliminary results, where we envision this as a more dynamic process. So you have some kind of a system, or ideally multiple systems, right? So this is something where these type of integrations can really save resources. They may share data, but you may have some local computation over this data. And then there is some framework that tells us what should be run and where. What should be run on the cloud, perhaps with a much larger model to make a decision. What should be run locally, perhaps because of time. So kind of like a reflex network here. I like to think of it like that. Very low latency tells us if some safety or there's some, or maybe there is we expect large latency from the cloud, so we want to run something locally. So this is something that you can see even these networks might do different things. They don't have to be that tied, but they need to be integrated synergistically. Maybe you have a hazard, so you have to perform something locally, and then maybe this local network kind of does some of the scheduling as well, like whether to run something locally, whether to run something on the cloud to send it. Maybe there's some prioritization. So this question of what, how, and where to run can really help us save a lot of these resources potentially. So we propose to formulate this as a Markov decision process, where the states are observations from the sensor data, battery state, perhaps some safety state, and potentially also cloud server state, right? So there's some things that run on the cloud, maybe some queues or prioritization that we should consider, especially when we scale these things. And then an action might be jointly thinking about the task, but also whether it should be processed locally or on the cloud, right? So imagine that I expect low latency or high latency that would influence my interaction with the world. So this should be acted jointly. And then there's some reward that comes from the task, like maybe we don't want to collide with something, or maybe we successfully fed assisted feeding and then disrupt social navigation and such metrics. So I want to show a basic preliminary demo. On the left here, we have a cloud-only model that runs on this really minimal system.
Ashad, before you do that, there's a question from Iran. I assume you can't see the
Sure.
The
By the way,
hands
I need to
while
get
you're
my laptop
presenting.
charger, but let me see. Sure. Should I answer it now? I have 2 more slides.
Oh, okay. All right. Go ahead then if you're afraid you're going to run out of charge.
Here, let me look at the question. Sorry.
Oh,
Oh,
he just raised his hand.
I
Okay.
just raised the hand. Actually, I'm sort of,
Sure.
there's cloud, which is sort of assumed something you have very low bandwidth to, and on sort of predictable latency, and then there's edge where you have a bunch of devices. But I keep thinking, like, if we had, say, at certain buildings at BU, a sort of deterministic local thing that is an extrusion of the cloud, if you like, that could be shared between things. Is that something in your equation? Like, you could imagine local resource at a building level, or at a that could be a shared resource with, say, more guaranteed latency and bandwidth?
That's a really good point. So what I like about this approach is that it's just going to optimize for the task. So we can set the states and add these things. I think one thing that is related to what you say is like Wi-Fi connectivity, right? Is that what you mean, Oran, by building?
I could imagine us easily setting up an infrastructure that's connected to local Wi-Fi, a small number of services in each building, right? If there's a variety of projects like this that would exploit that, that would be sort of an extrusion of the cloud and then reduce the data before shipping up to the thing that really has a lot less deterministic bandwidth to it and a lot higher variability.
For sure.
Is that a useful primitive that you could use if we had such a thing?
It is, yeah. Yeah, so I see. So almost as an assumption. So we know that the building has certain resources. How can we best leverage it?
Right, right. And it's limited, but it's shareable in some sense. It's something I could imagine from the systems, the OpenShift, whatever side, us developing. And I'm just curious if that would simplify and change the problem.
Wi-Fi simplified this significantly because it's such an important resource to have compared to other type of communication where suddenly the latency becomes highly variable. It can also vary inside a building. So maybe
Okay, I just wanted to pose that. This is something we talked about offline, but it's
Sure. I think it's interesting. Ideally, so I would just say that we want this model to kind of model what you're saying. So kind of try to predict. So in this clock here, there should be some model that tells me how long is this operation going to take if I'm going to send it to the cloud. And I think what you're saying can integrate here.
Yeah, I just don't think of the cloud as a fixed thing. We control it. So what you want in the cloud is an interesting question. I'd love to hear more about. I got to run to another meeting, but I just wanted to raise that as
sure. And then let me show you some results that I think also touch on this point. So on the left here, we have a cloud-only model, and you can see how there is latency, like you said. So in this case, this robot may get very close to the obstacle before making the decision because of this variable latency. And also kind of slowly react, to get back to the path. And then on the right here is an example of a switch that switches to local computation. So you can see how this is actually a pretty difficult task, running it with this minimal robot, but it definitely has some more of a proof of concept. And I think we want to further explore this. How do we standardize this? How can we create latency models that tells us whether the local policy needs to wait or needs to perform something sooner? and then what kind of the cloud state, and maybe we can even have the cloud assistance with adapting models. So maybe we can add a task here of adaptation. And I want to show something about the first part here, and that'll be the final slide, where we are actually, so here's an example of a policy where we're measuring the latency. And you can see in this policy, it actually learns to stop when it sees very nearby pedestrians. And what it does, you can see the latency goes up when it goes into cloud mode. But then locally, when it stops, it runs things. So it runs things locally because it detects some kind of a safety hazard and then goes back to the cloud operation. You can see this is a potential scenario that we're interested in. And I think with that, I'll finish. Happy to answer any questions.
Thank you, Ashid.
Sure, my pleasure.
Any other questions for Ashid? Well, thanks for fitting into the time limit, Ashid. I appreciate that. Anybody who's interested, please get in touch to follow up on these. Both of these projects are in the early stages, so they'd love to have more Red Hat and other people's collaboration. Thanks a lot, and we'll see you again next month.
Good job, everybody.